Okay, so this one says there's a function g defined on the closed interval from -4 to 8. Okay, and that's the graph of g up there. Okay, consists of two linear pieces and a semicircle. Let f be the function defined by that expression. Okay, so, and then they ask us to find f of 7 and f prime of 7. Okay, so let's find f of 7 first. So just plug in 7 for all the x's. This, okay. Okay, and then just keep in mind you interpret this as the area under the graph, or between the graph and the x-axis, from 0 to 7. So look at this, from 0 to 7. Okay, and so that would be, that would be all of this. Bigger. That would be like all this area here. That's from 0 to 6. Whatever that area is. And then this area, kind of add to it to find the whole area from 0 to 7. Okay, and then just keep in mind when we find this, just remember this is negative and this is positive. All right. All right, so this is a semicircle, and the radius is 3. And so if this was a full circle, this would be 9 pi. But since it's only half a circle, this area is 9 pi over 2. And this will be negative. And then we can see this other one's just -3. Just count those boxes. Or just 3. What am I talking about? Okay. So this is 21 minus 9 pi over 2, and then plus 3. Alright, so that's f of 7. And then f prime of 7. So for this one, we'll first have to find f prime of x. Okay, just take derivative. So derivative of 3x is 3. And then remember, if you take the derivative of an integral, there's a more general way, but if this is a constant and this is x, you just plug x into this function. So this is, instead of g of t, it'll be g of x. Okay, now we can plug in 7. And then find g of 7 up here. So g at 7 is 3. Okay, and we didn't need any explanation to get full credit, just show our work. Okay, find the value of x in the closed interval from -4 to 3. Okay, so that's only up until this point here, from -4 to 3, at which f attains its maximum value. Okay. So, good to categorize problems, because, this is a problem where they're asking for the maximum or minimum value on an interval. And so there's clear kind of steps to do that type of problem. So to find, absolute max or min on an interval, you find the critical points, and then you plug those and the endpoints back into the original. Okay, so to find critical points for any function, take derivative, and we've already done that. So f prime of x is 3 plus g of x. I'll rewrite that. Okay, and then we want to see where this is 0 or undefined. Okay, so this derivative will only be undefined if g is undefined. And so we can see, whoops, we can see here, g is not undefined anywhere. It's not continuous everywhere, not continuous at 6, but it's defined at 6, defined everywhere. And it actually doesn't matter anyways, it's only up until from -4 to 3. And so it's defined everywhere. Here it's not differentiable, but it's still defined. Okay, so this is defined everywhere. So the only thing we really have to do is set it equal to 0. Okay, if we do that, that means that g of x has to equal -3. And that happens when x equals 3. So x equals 3 is the only place where g equals -3. Okay, so wait, let me make sure I'm doing this right. So maximum value. So take derivative 3 plus g. Okay, yeah, so here, sorry, let me think. Oh, yeah. Okay, so we could kind of do this two ways. We could actually plug in values now. So here, we'll kind of do it both ways. So let's say you found, so now we realize the only critical value is at 3, and so we only have to really plug in the endpoints since a critical point is the endpoint. Okay, just remember we're plugging these back into the original because we want to see where f, the original function, we want to find out where that has a maximum or minimum. Okay, so we could actually plug these in. Actually, now that I think about it, let's not, just to save time. Kind of, yeah, we could do it. But look at this. So do you notice if f prime of x is 3 plus g? Wait, sorry. Yeah, if f prime of x is 3 plus g, do you notice this is always positive? Or it's the only time it's at least never negative, right? So this is never decreasing. And so since f prime is never negative, 3 plus g of x is never negative, then this function is always increasing, so the right hand endpoint should be the maximum. And so we just know that there's a maximum at x equals 3. And I'm going to do that. I'm just going to do that instead. That's better. And we'll just do our little explanation. Okay, so just say something like, since f is non-decreasing, on this interval, it must reach its maximum at the right endpoint, which is x equals 3. Yeah, so that's the best way. That's the best way to do that. Okay, we could plug in the two values, -4 and 3, and see which one's bigger. Either way, just saves time, I guess. Okay, this next one, same graph for each of those limits. Find the value or state that it doesn't exist. Okay, so let's find g prime of x. I should have written that, I think. So we had f prime of x. Actually, no, we don't need to. We can just look at the graph. Okay, so let's look at the graph. So if we want to find, so, g prime is our slopes, right? So we can see, like, from the left, first of all, this is a constant slope, right? So, like, as x approaches 0 from the left of the derivative, the slope is constant. And so, the slope of this line is -1/2. So this is -1/2. Like that. Okay, and then this slope, so limit as x approaches 0 from the right of g prime of x. So here's g of x, but we're looking at the slopes. What happens to the slopes of tangent lines as we get closer to 0 from the right? And we can see this slope is getting closer and closer to being, really negative infinity, which means it doesn't exist. So limit right does not exist. Circle that. Okay, and then the last question down here. Okay, so kind of like always, we'll plug in the limit first and see what happens. So if we plug in the limit, you get f of -2 plus 7 over e to the 0 minus 1. Okay, f of -2, and keep in mind the way f was defined. I'll write that above. Like that, okay. And so f of x, or f of -2, we'll have to find. Okay, so this will take a little bit of work. I'll do that below. -2 equals -6, and then plus 0 to -2. Okay, so I just plugged in -2 for the two x's, and then we'll start solving this. Okay, so keep in mind, we're going to eventually, we want to interpret this integral as finding area under the curve of the graph above. But the only way to interpret integrals as area is if the bottom limit is smaller than the top limit. And so we have to switch these limits. But then remember, when you switch the limits of an integral, you have to change the sign, or negate that value. So we'll do that. Okay, and then now this says we want to find the area under, or between the graph of g and the x-axis from -2 to 0. So let's do that. Okay, from -2 to 0, we can see this area. That's 1, 1/2 base times height. That's 1. Okay, so that'll be that. Oops. and that's just -7. And that'll make sense now. So now we realize this f of -2 up here is -7. And then e to the 0 is 1. So now we get 0 over 0. And we figured we'd get that. Okay, so this means that we'll do L'Hopital's rule. So I'll do that down here. So limit 2. So derivative of the top is just f prime of x. Derivative of 7 goes away. And the bottom, the derivative of that exponential function is derivative of the exponent. And then just rewrite the function. Okay, and then the -1, the -1 goes away up there. Whoops. Okay, so now we'll replug in the limit. Okay, if we plug in -2, that's 0 there. And then now f prime at 2, or at -2. Did we get that already? F prime at -2. Maybe not, but here, so there's f of x, and then we'll realize f prime of x, that. And so f prime at -2, g at -3 plus g at -2. Okay, g at -2 is 1. So this just equals 3 plus 1, which is 4. And so now that means that f prime at -2 is 4. And so we'll replace that. Over 3. And that's it. Yeah. Okay. Okay. So the next two problems go together. They both deal with this function. Okay, first they say write an equation for the line tangent to the graph of f at the point where x equals 0. Okay, so same thing every time. And actually, let me rewrite this just to, this is, okay, and I don't know if that should be less than or equal to, but it's going to be one of those. So that's what that just came out weird. Okay. Okay, write an equation for line tangent to the graph of f at the point where x equals 0. Okay. So find the equation of the tangent line means finding slope, which is derivative, and then finding the full point also. So we know the point's going to be 0 comma something, and just have to plug it in to find the y value. Okay, so it doesn't matter what we do first. Maybe I'll plug in 0 to get the y value of the point first. Okay, and then tan 0 is 0. And so that just is 1. Okay, and then now we have to find f prime, and then we'll plug in 0 into that also to find slope. Okay, so overall we'll do power rule. And then times by, and then we'll do chain rule. Derivative of tangent is secant squared. Okay, and then just remember now our slope is going to be f prime at the x value at 0. So this is just 1, and then secant squared is 1. So this is just 3/2. Okay, that's our slope. And so now we'll just equation the tangent line. So y equals, and so we got our slope, 3/2 x. And then just keep in mind this, so this happened to be, this is 0, 1. You know, 0, when you have 0, something, the y coordinate is the y-intercept. And so here, you know, mx plus b, that's the y, b is the y-intercept. And so that'll be it. Okay, and then for the approximation down here, now we'll just plug in 0.02 for x. And so, and then we're going to use that, using the equation right, to approximate f of 0.02. So f of 0.02 is approximately whatever we get when we plug in 0.02 into the tangent line. Okay, and then, you know, 0.02 is 1/50. And I'm going to simplify. I know we don't have to, but whoops. Okay, so this is 3/100 plus 1. And then 3/100 is 0.03. So this is 1.03. And that's it. Okay, and but just keep in mind, you could have written that and gotten full credit. So don't have to simplify, just have to solve for the thing itself. Okay, so the next 4 problems, I'll deal with this chart up here. So, okay, Ben rides a unit cycle back and forth along a straight east-west track. The twice differentiable function b models Ben's position on the track measured in meters from the western end of the track at time t, measured in seconds from the start of the ride. The table gives values for b of t and Ben's velocity v of t measured in meters per second at selected times t. Okay. Use the data in the table to approximate Ben's acceleration at time t equals 5. Indicate units of measure. Okay. You know, acceleration is derivative of velocity. But to approximate, you know, we don't have a function, so we can't take derivative of the velocity since we don't have a velocity function. But if we look at this, so t equals 5, you know, right in between 0 and 10. So if we can find, like, basically the average acceleration on like this interval from 0 to 10, that'll approximate the acceleration when t equals 5, like in the middle. So we'll do that. And now to find the average acceleration on an interval, you'll do slope formula with velocities, almost like you're taking derivative. You know, doing slope formula with a function gives you the same type of thing as if you took the derivative. You know, like if we do slope formula with velocity, it gives us acceleration. Just like if we did derivative of velocity, that gives us acceleration. Okay, so we'll do it with, you know, these will be our y values and these will be our x values when we do slope. So let me write this. Whoops. Let me write this down here. Okay. Okay, Ben's acceleration. Okay. So the acceleration at 5 is approximately approximately 0.03 meters per second squared. Okay, next one. A light is directly above the western end of the track, okay, where they start. Ben rides so that at time t, the distance L of t between Ben and the light satisfies that equation. Okay, so it's some kind of triangle. It's like a Pythagorean theorem, I guess. So at what rate is the distance between Ben and the light changing at time t equals 40? Okay, so hopefully you see that this is a related rate type question. Wait, let me make sure about that. Oh, no, sorry. No, this isn't related rate. These functions are in terms of t, so it's not a related rate. Okay, we'll just take derivative. So at what rate is the distance between Ben and the light changing at time t equals 40? Since L of t is the distance between Ben and the light, L prime of t will be the rate that it's changing at any given point in time. So what we really want to find, we want to find L prime of 40. Okay, so let's start taking the derivative of this equation, and we'll get a L prime of 40 out of it when we do chain rule here, or L prime of t, and then we'll plug in 40. Okay, so if we take derivative, we get 2 times L of t times L prime of t. Okay, derivative 12 squared is 0, and then the 2 b of t times prime of t. Okay, I'm going to cancel out those 2's, and then I'm going to plug in 40 for all the t's. Okay, and then now we have to solve for this. So hopefully we can get these other 3 values, and then we'll solve for L prime of 40. Okay, L of 40, oops. Okay, B of 40 and B prime of 40 we will get from the chart. L of 40 we'll get by plugging in 40 into the original, and then we can get L of 40 that way. Okay, I'm going to do that off to the side. Okay, so that means that L of 40 equals the square root. And then we'll go up to B of 40. B of 40 is 9. You can see at 40, B is 9. And so this is 9 squared, which is 81. Okay, and then you add those, that's 225. And so that's 15. Okay, so now go back to here. So we found L of 40, that's 15. Okay, and then B of 40 and B prime of 40. So B of 40 is 9, B prime of 40 is 2.5. Right, this is B at 40, B prime of 40. So 9 times 2.5. And then now just divide both sides by 15. And that's the answer. Okay, so keep in mind you could just leave it like that, right? You've solved for L prime of 40 like they asked. Okay, but here I'll simplify it just in case someone else did. So times top and bottom by 2, so 27 over 30. Wait, 35 over 30. Oh, okay. So that would be 7/6. So you could write either one of these. Wait, did I do that right? Wait, that's 5. Oh, 45/30. It's 3/2. Okay. Okay, just keep in mind this is meters per second. We'll have to add those units. Alright, so that's those two. Alright, and these two both deal with the same chart. Okay, so that says for t between 40 and 60, there must be a time t when Ben's velocity, or must there be a time t when Ben's velocity is 2 meters per second? Justify your answer. Okay, there's two possible ways that a question like this could be answered. First is intermediate value theorem. If anytime they're asking it for like the existence of something, if something exists, you're almost always going to use a theorem. They have these things called existence theorems, and that's what the intermediate value theorem says. It says if the function's continuous, and we know since it's differentiable, so it has to be continuous. But if a function's continuous, then it takes on all the y values, like from 40 to 60. We'd be looking at, this, and we'd really be looking at these y values. So do you see from 40 to 60, from 40 to 60, the function at 40, the velocity is 2.5, and at 60, the velocity is 4.6. So the intermediate value theorem says that the function will equal any value between, any value between 2.5 and 4.6 on this interval. So they're just saying like 3 is in between here. So somewhere between 40 and 60, the velocity will be 3, or 3.5, or 4, or 4.5. Okay, but the problem with this one is, so that could have been the way we did it, but the problem is that 2 isn't between 2.5 and 4.6, so that doesn't help us. Okay, so we'll have to do it a different way. So we can do the mean value theorem. So mean value theorem says whatever the slope is of the secant line between the secant line between the endpoints of a function, the function, the derivative, there has to be a point on the same interval where the derivative equals the slope of the secant line. And so that's like this formula here. Right, so it's saying there exists some x value they call c, so that the derivative equals the slope of the secant line on the endpoints. Because this is the interval from A to B. Okay, so let's do that. So now we'll use, if we want to talk about his velocity being 2 meters per second, when we're doing mean value theorem, we'll have to use position values. Okay, so for this one, we'll do 49 minus 9 over 60 minus 40. And then that's 2. So that worked out, that has to work out just right. These have to be the exact same things. All right, and then now we have to just figure out how to write this. So if you look at the theorem, the mean value theorem, you'll just have to show that this function satisfies the hypotheses of that theorem. And so I think it says, well, it has to be definitely continuous on the closed interval, and then it has to be differentiable on the open interval. So you can say, since B of t is continuous on this interval and differentiable on, oh, this should be, what am I doing? This should be a closed interval. Differentiable on the open interval. The mean value theorem. Oh, and then put, sorry. Okay, so then, and then we'll say and, something like this. And, since f of 60 minus f of 40 over equals 2, the mean value theorem guarantees that there exists a time t between 60 and 40 such that f prime at t equals 2. Alright, so something like that. And I should have used b's instead of f's, but so yeah, I should have done that. So really all these, here, I'm going to try to be better about not being so shorthand. So really this should be, these should all be b's instead of f's. Okay, is that right? Yeah, okay. And then up here also. Okay, so I think that's that'll get full credit there. Okay, next one. Using correct units, interpret the meaning of, and so that they mean 0 to 60, absolute value of V of t. Okay, in the context, so interpret the meaning of this in the context of that problem. Okay, so just remember, if you take an integral of velocity, it's going to give you some type of position. It's going to have something to do with position. And so this case, any time you take an integral of absolute value of velocity, that's really total distance traveled. And so in the context of this problem, this is a unicycler. So we could say something like the unicycler or you could say something like this is the total distance traveled by the unicycler in the first 60 seconds. Okay, so there's something like that. Okay, and then they say also approximate this using a left Riemann sum with the subintervals indicated by the data in the table. Okay. Okay, so we'll do LRAM for this one. Let me erase all this. Okay, so LRAM. Okay, so just keep in mind, so here we have like this that first subinterval. So here we have 3 subintervals from 0 to 10, 10 to 40, and 40 to 60. And what do they want? Yeah, VFT. Okay. Okay. So so we're going to use these values again. Okay. But if we're going to use if we're doing LRAM, so keep in mind the width of the center of the subinterval is 10, and that would be the width of the rectangle, because these are all rectangles that, you know, we're adding areas of rectangles together. So the width would be 10 of the rectangle in the first subinterval. The height is going to be dictated by the value out on the left, which is at 0, and so that's just 2. And then we'll just do that for each subinterval. So now, okay. Okay, so now we'll do the exact, oops, sorry, I'm struggling. Now we'll do the same thing with the next subinterval, this one, and we'll use that value. Okay, so now the width of this subinterval is 30, right? 40 minus 10, and then we'll use 2.3 as the height of that one. And then for the last one, the width is 20, just doing 60 minus 40, and then the height we'll use is 2.5. And just 20 plus 69 plus 50. Okay, so this is 139. Okay, so now since we did that, we can say this. Okay, and then this will be meters. Okay, yeah, so that's everything. All right, so we have the last problem. Okay, so the first time we've done one of these in a while, I think. Okay, let G be the function defined by that. Let R be the region of the first quadrant bounded above by the graph of G on that interval. Okay. Okay, so this is just from 0 to 4. Okay, and then the graph of square root of 6x. So at 0, it's 0. At 4, it's square root of 24, which is a little less than 5. So we'll call that 5. So that's a little less. And then this just looks like a square root function. And then, so now they say let R be the region in the first quadrant, bounded above by the graph of that. Okay. So the area that we're looking for is this, just this area here. All right, so we're going to do an integral 0 to 4, and since it's just the area underneath a function, between a function and the x-axis, then we can just integrate that function. So really it's going to be 6x to the 1/2 dx. Okay, and then I'm even going to rewrite this a little differently. So you get, we could, this 6x to the 1/2 is like 6 to the 1/2 times x to the 1/2. So that's just square root of 6 times x to the 1/2. Okay, so I'm going to rewrite it like that and pull out the square root of 6. Okay, so now this will just be square root of 6. Okay, take the integral, so we'll get an x to the 3/2, but then, if we took the derivative of this, we'd have to cancel out the 3/2. So that's 2/3. And then evaluate that from 4 to 0. Okay, plug in 4, you get 2/3. Times 4 to the 3/2. And that'll be minus 0, so that's just really that. Okay, and then keep in mind, this, you could write the answer just like this. This is perfectly fine. But just in case you did simplify it, you would get square root of 6 times 2/3. And then 4 to the 2/3. Remember, it's like square root of 4, which is 2, and then 2 cubed, which is 8. And so this would be something like 16 root 6 over 3. So you could do that also. Okay, but remember, I would leave it like that. Just, you don't get any extra points for simplifying. You can only get points taken off. So, okay, part B. Let that same region be the base of a solid, and then for this solid, each cross section perpendicular to the x-axis is a semicircle whose diameter lies in R. Whoops. Okay, so let me duplicate this real quick and bring it down. Okay, so they say each cross section perpendicular to the x-axis, so perpendicular, take a cross section, is a semicircle whose diameter lies in R. So it's all like, these will all be like semicircles, that come out here like this. If they were a full circle, they'd kind of come back down, but we're just looking at the tops of these, so these are all just semicircles here. These would be little semicircles, and just kind of keeps going. Okay, so whenever they describe cross sections like this, it's not one of those rotating ones. Just remember that the way to find it is do area from A to B, or integral from A to B of the area, some area function, and the area represents the area of a cross section. And we're looking at really kind of the area of like this cross section here, just the top half. Okay, so the area of that is a semicircle. So for us, we know we're going to do integral, definitely from 0 to 4 on that, just the x values of the graph, where the region lies. And then we're going to have to do some kind of like a pi r squared over 2, like that. And it's really that r that we have to get in terms of x. And just keep in mind, all these semicircles are different, right? So they all have different radiuses, and that depends on what x is. So think about the diameter is the function, right? Whatever the function equals at an x value, that's this distance. And so we really have to take half the function. So really our r is half of this function. Okay, and so that's the radius that we'll put here. Okay, when we square the square root, actually here I'll just rewrite it first. Okay. Okay, I'll clean it up a little bit. So this will become a 1/4 when you square it. The square root will go away. So, and that'll just have a 6, 6x. And so we'll have, on the outside, we'll have like a half times 6, and then that pi can come out over 2. And this will just be the integral. Okay, so hopefully you see, oh, and that should be a 1/4. Whoops. Okay, so just keep in mind, so this 1/2, when you square it, becomes a 4th. When you square, this square root goes away, so this 6 you can pull out, this pi you can pull out, and this 2 you can pull out. Okay, so now I'll clean up this integral a little bit. So this will be 3 pi over 4. And then we'll integrate. Okay, and then when we plug in 4 squared is 16 over 2, which is 8. And then minus 0 is just 8. That's 6 pi. And do we need units? No. Okay, so make sure, yeah. Okay, and then last one. Okay, let f be an antiderivative of g. Oh yeah, okay. Find the length of the graph of f from 0 to 4. Okay. Okay, so here we'll do arc length. Okay, so let's just start with the arc length formula and then we'll go from there. So arc length. Okay, so that'll be the integral from a to b. Blow this up a little bit. Oops. Okay, so that'll be integral from a to b, square root of 1 plus the derivative of the function squared. Now we want to find the length of the graph from 0 to 4. The integral from 0 to 4. We'll do 1 plus the length of the graph of f. So that'll be actually f prime of x. That's like this exact same thing. Okay, and then if they say that f is an antiderivative of f, that means that if f is an antiderivative of g, that means g has to be a derivative of f. So this derivative of f becomes g. And it's just g, not g prime. That. Okay, and then now we can plug in, what was g? Square root of 6x, yeah. Now we can plug in g. I'll change this to the 1/2. So this will be 1 plus. Since g of x is square root of x, this will square root of 6x, this will just be 6x. Okay, now we integrate that. Go off to the side here. Okay, so we know we're going to get a 1 plus 6x to the 3/2. If we took the derivative of that, we'd have to cancel out the 3/2 with the 2/3. And we'd have to, if we took derivative, we'd get a 6 from the chain rule, so we'll have to cancel out that 6th. 6 with a 1/6. Okay. All right, and then 2/3 times 1/6 is 1/9. So I'll kind of pull that out. All right, and then we'll plug in 4. So we'll have 25 to the 3/2 minus, and then plug in 0. So we'll have 1 to the 3/2. 25 to the 3/2, so it's like square root of 25 is 5. 5 cubed is 125. 124 over 9. They don't give any units, do they? Yeah, no. Okay. All right, so that's it. Okay, let me make sure that's right. Yeah, okay. Yeah, that's everything.